419 million years ago, Earth's continents were bare rock. No trees, no soil, no forests, just stone stretching to empty horizons. The oceans, by contrast, were packed with life. Armored predators the size of buses patrolled warm, shallow seas. Reefs thousands of miles long sprawled across flooded continents. Atmospheric carbon dioxide sat at 4,000 parts per million, 14 times higher than today's levels, trapping heat like a planetary blanket. This was normal. This was stable. Then plants learned to grow tall, to dig deep, and to build wood. Within 20 million years, 75% of all species on Earth were dead. The Devonian period stretched from 419 to 359 million years ago. For most of that span, life on land barely existed. Early in the period, plants hugged coastlines and riverbanks, small, leafless, rootless organisms that looked more like branching green sticks than anything recognizable as vegetation today. They belonged to groups like Rhynia, pioneers that could tolerate brief exposure to air but never strayed far from water. The real action was offshore. The oceans were a hothouse. Carbon dioxide levels hovered around 4,000 parts per million, sustaining a greenhouse effect that eliminated polar ice caps entirely. Sea levels rose so high that shallow seas flooded deep into the continents, creating vast inland waterways across what would become North America, Europe, and parts of Gondwana, the supercontinent that held the future southern landmasses. Water temperatures in these tropical shallows could exceed 30 degrees Celsius. There was no seasonal ice anywhere on the planet. This warm, stable world belonged to groups of animals that no longer exist. The dominant predators were plecoderms, armored fish whose heads and front bodies were encased in interlocking bony plates. The largest, Dunkleosteus, stretched 10 meters long and weighed 4 tons. Its jaws were not teeth, but self-sharpening bony blades that closed with enough force to crack through other armored fish. Placoderms had ruled the seas for tens of millions of years, diversifying into bottom feeders, filter feeders, and apex hunters. Beneath them, the seafloor hosted sprawling reef systems built by stromatoporoids, massive sponge-like organisms, and 2 groups of ancient corals called rugose and tabulate corals. These reefs stretched for hundreds of kilometers, creating habitats for trilobites, brachiopods, and the earliest ammonoids. Sharks and ray-finned fish existed, but they were minor players. The Devonian Ocean was optimized for a specific set of winners, and those winners had held their positions for geological ages. Above the waterline, the continents offered almost nothing. By the Late Devonian, roughly 375 million years ago, that barren landscape had transformed. Forests now covered Euramerica and stretched across parts of Gondwana. These were not the forests of mosses and ferns that would come later, nor were they the conifer and flowering plant forests familiar today. They were dominated by a single revolutionary organism, Archaeopteris. Archaeopteris was a progymnosperm, an evolutionary precursor to seed plants. It stood 20 to 30 meters tall, as high as a 10-story building, with a woody trunk up to 1.5 meters in diameter and a crown of fern-like fronds that spread wide to capture sunlight. It was the first organism on Earth to look like what we would call a tree. More importantly, it was the first to behave like one. 3 evolutionary innovations made Archaeopteris a geological force. The first was lignin, the complex organic polymer that stiffens plant cell walls and allows vertical growth. Lignin made wood possible. With it, plants could grow tall enough to compete for light without collapsing under their own weight. The second innovation was leaves, broad, flat surfaces optimized for photosynthesis. Earlier plants had relied on exposed stems for gas exchange. Leaves were vastly more efficient. The third, and ultimately most destructive, innovation was deep roots. Before Archaeopteris, plant roots were shallow, thread-like structures that anchored organisms near the water's edge. Archaeopteris roots burrowed meters into bedrock, splitting stone apart as they searched for moisture and nutrients. These roots were not passive. They secreted organic acids, compounds that dissolved minerals like calcium, magnesium, and potassium from the surrounding rock. This was chemical warfare on a microscopic scale, conducted by millions of trees across millions of square kilometers. The rocks themselves were being digested. For the first time in Earth's history, the continents had soil. Not the thin crust of decayed organic matter that had accumulated near shorelines, but deep, layered soil held together by root networks and enriched by the breakdown of bedrock minerals. This soil retained water. It supported fungi and the first terrestrial arthropods, mites, springtails, early relatives of insects. It turned barren stone into a substrate capable of sustaining ecosystems, and it began to alter the planet's chemistry. The relationship between roots and rock is a chemical reaction. When Archaeopteris roots secreted acids into cracks in granite or basalt, those acids broke molecular bonds in silicate minerals. The reaction released calcium and magnesium ions, which dissolved into groundwater and eventually flowed into rivers and then into the oceans. This process, called silicate weathering, is natural. It happens wherever water and rock meet. But before the evolution of deep-rooted plants, it happened slowly. Archaeopteris forests accelerated silicate weathering by orders of magnitude. Root systems increased the surface area of rock exposed to chemical breakdown. Soil, by retaining moisture, kept the rock-acid interface wet for longer periods. The result was a planetary-scale increase in the flux of calcium and magnesium into the ocean. In seawater, these ions combine with dissolved carbon dioxide to precipitate out as calcium carbonate. These minerals settle on the seafloor as limestone, locking atmospheric CO₂ into rock permanently. Silicate weathering, turbocharged by plant roots, became a carbon sink. At the same time, the forests were pulling carbon dioxide directly from the atmosphere through photosynthesis. Archaeopteris used carbon dioxide, water, and sunlight to build cellulose and lignin, the structural materials of its trunk and leaves. When trees died and were buried by sediment in floodplains or peat in swamps, the carbon stayed buried. Decomposition couldn't proceed without oxygen. Burial meant permanent removal. Late Devonian rock layers contain the oldest extensive coal seams on Earth. These are compressed, carbonized Archaeopteris forests. The same period also shows thick deposits of black shale, fine-grained sedimentary rock rich in organic matter. Both are carbon graveyards. The two mechanisms, direct photosynthetic drawdown and root-enhanced weathering, operated simultaneously. One was fast, pulling carbon out of the air in decades. The other was slower, operating over millennia, but relentless. Together, they dismantled the carbon cycle that had kept the planet warm. Atmospheric CO₂ began to fall. Estimates suggest it dropped from 4,000 parts per million to somewhere near 300 to 400 parts per million, a decline of roughly 90%. The greenhouse blanket that had insulated Earth for tens of millions of years was disintegrating. The forests didn't stop. Archaeopteris spread across every available landmass. By the middle of the Late Devonian, vast swaths of Euramerica, the region that would become eastern North America and western Europe, were covered in dense, continuous forest. Gondwana's northern margins, which stretched across the equator, supported their own stance. Pollen and spore records from this period show an explosion in the diversity and abundance of land plants. The fossil record preserves root structures that extend more than 3 meters into bedrock, far deeper than anything seen in earlier periods. The rate of carbon burial accelerated. Sedimentary basins filled with plant debris. Swamps, which formed in low-lying coastal areas and river deltas, became particularly effective carbon traps. Waterlogged conditions slow decomposition. Dead plant material piled up faster than it could rot. These swamps would eventually compress into coal seams dozens of meters thick, particularly in what is now Pennsylvania, West Virginia, and parts of Canada. Carbon isotope ratios from Late Devonian rocks provide chemical evidence of this burial. Plants preferentially take up lighter carbon-12 during photosynthesis. When massive amounts of plant material are buried, the remaining carbon in the ocean and atmosphere becomes enriched in heavier carbon-13. Late Devonian marine carbonates show exactly this shift, peaking just before the first major extinction pulse. The signal is global, confirming that unprecedented amounts of organic carbon were being removed from the active carbon cycle. The atmospheric consequences were immediate on a geological timescale. Carbon dioxide is a greenhouse gas. Remove 90% of the CO₂, and you remove 90% of that heat retention. Global temperatures began to drop. The tropics cooled, mid-latitudes became seasonally cold, and at the poles, particularly over Gondwana, which was drifting across the South Pole during this period, conditions became suitable for ice. The creation of soil had a second consequence. For the first time in Earth's history, the continents had a layer of organic-rich material that could be eroded. Rainfall no longer just washed bare rock. It washed soil, carrying dissolved nutrients, particularly phosphorus and nitrogen, into rivers and eventually into the oceans. This runoff was planetary-scale fertilization. Phosphorus and nitrogen are limiting nutrients for marine photosynthetic organisms. In most oceans, they're scarce enough that algae and cyanobacteria populations remain relatively stable. Introduce a sudden influx, and those populations explode. The Late Devonian oceans received exactly that influx. Rivers draining the new Archaeopteris forests dumped nutrients into the warm, shallow inland seas at concentrations never before seen. The result was algal blooms of unimaginable scale. Surface waters turned green and thick with microscopic life. These blooms were not localized events. They were ocean-wide. When the algae died, either from nutrient depletion or from overcrowding, their bodies sank to the seafloor. There, bacteria gathered to decompose them. Bacterial decomposition consumes oxygen. The more organic matter there is to decompose, the more oxygen gets used up. In the Late Devonian, the amount of organic matter raining down on the seafloor overwhelmed the oxygen supply. The bottom waters went anoxic, depleted of dissolved oxygen. Fish, invertebrates, anything that needed to breathe, suffocated. The anoxia spread. Shallow seas, which had been rich in life, became dead zones. The water likely turned toxic, reeking of hydrogen sulfide, the same chemical that gives rotten eggs their smell, as bacteria switched to sulfur-based metabolism in the absence of oxygen. Creatures that couldn't swim away from the bottom died in place. The geological evidence for this event is unambiguous. Around 372 million years ago, at a moment called the Kellwasser event, black shale layers appear in sedimentary sequences around the world. These shales are black because they're packed with organic carbon, the remains of the algae and other organisms that died and sank into oxygen-free water. Without oxygen, the carbon couldn't decompose. It accumulated, layer upon layer, preserved in the rock record as a chemical signature of suffocation. The Kellwasser black shales appear in North America, Europe, North Africa, Australia, and Asia. Their global distribution confirms this was not a local catastrophe. The oceans had stratified. A thin surface layer, churned by waves and exposed to air, retained some oxygen. Everything below became a graveyard. Reefs, which had dominated shallow marine environments for millions of years, collapsed. The stromatoporoids and rugose and tabulate corals that built them were sessile organisms. They couldn't move. When the water around them lost its oxygen, they died where they grew. The Kellwasser event wiped out the reef ecosystems almost entirely. The planet limped on for another 13 million years, but the climate system was broken. Carbon dioxide levels continued to fall as forests expanded and weathering intensified. The oceans remained unstable, lurching between periods of partial recovery and renewed anoxia. Marine biodiversity, already devastated by the Kellwasser event, struggled to rebound. And then the temperature dropped far enough to trigger the second catastrophe. Gondwana, the massive southern supercontinent, had been drifting across the South Pole throughout the Late Devonian. When atmospheric CO₂ was high, this positioning didn't matter. The greenhouse effect kept even polar regions relatively warm. But with CO₂ levels now near or below 400 parts per million, the South Pole became cold enough for ice to accumulate. Snow that fell didn't melt. It compacted into glaciers. The glaciers spread, thickening into ice sheets that eventually covered millions of square kilometers of Gondwana. Ice has a feedback effect. It reflects sunlight back into space, cooling the planet further. The more ice there is, the colder it gets, and the more ice forms. By 360 million years ago, Gondwana was locked in a full-scale ice age. Glacial deposits from this period, tillites and striated bedrock, appear in South America, particularly Brazil, confirming the extent of the ice sheets. The ice locked up water. Oceans are a closed system. If a significant portion of water gets trapped as ice on land, sea levels must fall. During the Late Devonian glaciation, global sea levels dropped by an estimated 100 meters or more. That's over 300 feet. For a planet whose continents were covered in shallow inland seas, this was catastrophic. The shallow seas drained. The vast, warm marine habitats where life had retreated after the Kellwasser event disappeared. Coastal ecosystems were left high and dry, exposed to air. Reef remnants, already stressed and fragmented, lost the water they depended on. Fish populations that had survived the anoxia now had nowhere to live. The sea level drop didn't just remove habitat, it eliminated entire marine environments. This second pulse, called the Hangenberg event, occurred right at the boundary between the Devonian and the following period, the Carboniferous, around 359 million years ago. Like the Kellwasser event, it left a black shale layer, suggesting another episode of anoxia, possibly triggered by changes in ocean circulation as cold polar water disrupted global currents. The Hangenberg black shales are thinner and less widespread than the Kellwasser shales, but they mark the final blow to Devonian marine life. The extinction statistics are stark. An estimated 75% of all species disappeared. Some estimates place vertebrate losses even higher, above 95%. The crisis had lasted roughly 13 million years, from the first Kellwasser pulse to the final Hangenberg collapse. It was not a single bad day. It was a prolonged unraveling, driven by the systematic dismantling of the ocean's life support systems. The extinction was selective. Certain groups vanished completely, others barely noticed. The pattern reveals what mattered during a crisis driven by anoxia and habitat loss. Placoderms went extinct. Every species, every lineage, every evolutionary experiment within that group disappeared. Dunkleosteus and its armored relatives, which had dominated marine ecosystems for tens of millions of years, left no descendants. Their heavy armor, once an evolutionary advantage, may have been a liability. Armored fish are less efficient swimmers. They require more oxygen to maintain metabolic functions. In low oxygen environments, they would have struggled. The placoderms are one of the most complete extinctions of a dominant group in the entire fossil record. The great reefs were gone. Stromatoporoids, rugose corals, and tabulate corals, groups that had built the marine architecture of the Devonian, collapsed. Reef ecosystems of comparable complexity would not appear again for over 100 million years, not until new types of corals evolved in the Triassic period. The loss of the reefs cascaded through the food web, eliminating habitat for thousands of other species. Trilobites, already in decline before the Late Devonian, were decimated. Only a handful of groups survived into the Carboniferous, and those were shadows of the diverse, abundant populations that had characterized earlier periods. The Kellwasser event, which targeted bottom-dwelling organisms, hit trilobites particularly hard. Brachiopods and ammonoids suffered massive losses in diversity, though some lineages persisted. The victims shared characteristics. They were overwhelmingly marine. They were tropical or subtropical, adapted to warm, stable temperatures. They were shallow water organisms, living in the inland seas that drained during the Hangenberg glaciation, and many were bottom dwellers, making them vulnerable to anoxic conditions. The survivors were different. Sharks and ray-finned fish, though they took losses, came through comparatively intact. These groups were more mobile, more adaptable, and better suited to navigate unstable conditions. With the placoderms gone, an enormous ecological vacuum opened. In the Carboniferous, sharks and ray-finned fish would explode in diversity, filling niches left empty by the extinction. The modern structure of ocean ecosystems, dominated by cartilaginous and bony fish, was established by this reset. Land plants were almost entirely unaffected. Archaeopteris and its relatives continued to spread. The Carboniferous period, which followed the Devonian, would be even more heavily forested, covered in giant ferns, club mosses, and early seed plants. The organisms that caused the extinction thrived. Terrestrial life in general was spared. The extinction was a marine catastrophe. The collapse of ocean ecosystems had little direct impact on the emerging terrestrial ecosystems. And then there were the tetrapods, Creatures like Acanthostega and Ichthyostega lived right at the boundary of the Devonian and Carboniferous. They were four-limbed vertebrates, descended from lobe-finned fish, with adaptations for both water and land. They had lungs, allowing them to breathe air. They had limbs capable of supporting their weight on solid ground, at least briefly. They lived in coastal swamps and river deltas, exactly the environments most affected by anoxia and sea level changes. Traditional narratives frame the move to land as a conquest, an evolutionary step toward exploiting a new, resource-rich environment. But the Hangenberg event offers an alternative explanation. The water was becoming unlivable, dissolved oxygen was plummeting, shallow aquatic habitats were disappearing. The ability to leave the water, to haul out onto mud or rock and breathe air, was not an adaptation for exploration. It was an escape route. The tetrapod lineage, the lineage that would eventually give rise to amphibians, reptiles, mammals, and birds, may have survived the Late Devonian extinction, not by moving toward something, but by fleeing something. Scientists reconstruct this ancient catastrophe from fragments. The rocks themselves are the primary archive, and they contain multiple lines of converging evidence. Black shales are the most visible. The Kellwasser and Hangenberg black shales appear in sedimentary sequences on every continent that was underwater during the Late Devonian. Their dark color comes from unoxidized organic matter, carbon that accumulated in the absence of oxygen. The shales are often finely laminated, indicating that bottom waters were so anoxic that even burrowing organisms, which normally churn through sediment, couldn't survive. The organic content and laminations together are diagnostic of anoxic conditions. Glacial deposits provide evidence of the Ice Age. In South America, particularly in Brazil, geologists have identified tillites, chaotic mixtures of rock fragments deposited by glaciers, and striated bedrock, where moving ice sheets drag stones across the surface, carving deep parallel scratches. These features are unmistakable. They appear in rocks dated to the very end of the Devonian, confirming that Gondwana was under ice during the Hangenberg event. Carbon isotopes reveal the burial of organic matter. When plants and algae, which preferentially incorporate carbon-12, are buried en masse, the remaining carbon in the ocean and atmosphere becomes enriched in carbon-13. Geochemists measure the ratio of these isotopes in marine carbonates, shells, limestone, and track how it changes over time. At the Kellwasser and Hangenberg horizons, the carbon-13 ratio spikes. This positive excursion is a global signal of massive organic carbon burial, matching the hypothesis that algal blooms and forest burial were removing carbon from the active cycle. Oxygen isotopes function as a paleothermometer. The ratio of oxygen 18 to oxygen 16 in fossilized material varies with temperature. Scientists extract these ratios from the teeth of conodonts, tiny eel-like vertebrates whose hard phosphatic elements preserve isotopic information. Oxygen isotope data from late Devonian conodonts show a clear cooling trend, with temperatures dropping sharply into the Hangenberg glaciation. The fossil record provides the most direct evidence. Walk up to a cliff face exposing late Devonian strata, and the extinction is visible. Below the Kellwasser horizon, the rock is often limestone, packed with diverse fossils, reef structures, placoderm plates, trilobite exoskeletons, abundant brachiopod shells. At the Kellwasser black shale, diversity collapses. The shale itself contains few fossils, and those present are often disaster taxa, hardy, opportunistic species that tolerate extreme conditions. Above the shale, life slowly returns, but it's different. The reefs are absent. The placoderms are gone. The brachiopod species are new. This pattern repeats at the Hangenberg horizon. The fossil record doesn't just suggest mass extinction, it documents it, layer by layer. The Devonian extinction was Earth's first life-driven climate catastrophe. An evolutionary innovation, deep roots, efficient photosynthesis, the ability to build wood, gave plants access to new resources and new environments. That same innovation hijacked the planetary carbon cycle, drawing down atmospheric CO₂ at a rate the Earth system couldn't compensate for. The result was a cascade of environmental collapses, nutrient runoff triggering anoxia, falling CO₂, triggering glaciation, glaciation draining the seas. Life destabilized the systems it depended on. The lesson is specific but transferable. Planetary systems have tipping points. They operate on timescales that dwarf individual lifespans, or even species lifespans, which makes their momentum easy to underestimate. The Devonian CO₂ crash played out over millions of years, but once it began, it was difficult to stop. Feedback loops, ice reflecting sunlight, anoxia spreading through stratified oceans, amplified the initial perturbation. Today, we're running the experiment in reverse. The coal seams laid down during the Late Devonian, the compressed remains of Archaeopteris forests, are being burned as fossil fuel. The carbon they locked away 370 million years ago is being returned to the atmosphere. Atmospheric CO₂ has risen from pre-industrial levels of around 280 parts per million to over 420 parts per million today, a climb of 50% in 2 centuries. The Devonian teaches that carbon cycles have momentum, that ecosystems respond on timescales mismatched to human perception, and that tipping points, once crossed, are difficult to reverse. The mismatch between geological cause and biological effect is where catastrophes hide.